So this little video is talking about prime factorization. So we have this theorem. This is from another video, right? Any whole number n bigger than 1 can be written in terms of primes. Okay, and this is a unique representation up to like rearranging the order of things. So what is really kind of sort of powerful about this is we can take any number. Let me just say, I'm going to say n is, say, 56 to start with, right? And what we want to do is figure out all the primes on it. So one thing we could do is we could realize that, okay, 56 is 2 times, 28. Which is 2 times 14, which is 2 times 7, right? And so this is my, what's called prime factorization, right? And we can write it, and more often than not, we'll write it like this. So this is the prime factorization. Okay. So, we've got that. Now, how do we go about doing this? Well, what you can keep doing is you can keep, one way to do this is to, all I was doing is looking for, I started with 2 because 2 is the smallest prime, right? And eventually everything popped out, right? And if 2 wasn't it, then we could go to 3s or 5s or whatever. There's a little bit better way. This is called the factorization tree. And that is if I say, I'm going to start with 56 again. And I just want to, like, let's remember anything about 56. Well, the sort of most logical thing is its product is 7 times 8. And you got to remember, when we're doing this little tree here, these are all products. Okay, we saw these little trees with addition way back, so, but that's not what we're doing here. Okay. 7's prime. So we're going to break 8 down into 2 and 4, and then take 4 and break it into 2 and 2. And then we just sort of count everything up. So 56 we can write as 2, 1, 2, 3 of them, cubed, times 7. So this is the big thing that we typically will do with this. Okay, let's look at something else. I'm going to say 288. And we're going to write the prime factorization of it. Okay. So if it's not, usually you want to pull out something fairly big. It's maybe not clear. The 2 definitely goes into that in 144, hopefully. And again, you're starting to see a bunch of mental math here on this stuff. And we've got that. Now, the reason I did that first is I sort of saw that 144 was that. And 144 should recognize, right, as 12 times 12. And then 4 I can write that way. So 288 equals 1, 2, 3, 4, 5 2's, so 2 to the 5th, 3 squared. Right. Okay. So we've got that. All right. Now let me grab even a little bit of bigger one. I'm going to say 14,025 and write it as a prime factorization. Okay, well, with this, so some of the mental math may be like, all right, this is a little tough, but you should recognize it's a multiple of 5. You could probably maybe even guess it might be a multiple of 25. There's a little divisibility theorem that says if the last 2 digits are divisible by 25, it's divisible by 25. And so let's take a look at that. And so I will actually do the long division here. 25 into 140 should be 125. 6, 150, 1. Okay, so my first breakup is into 561. Right. Now I could have chosen 5 first, but it's a little bit faster to get through these things if you can find something bigger than it to start with. Okay, so I'm looking at this, and there's a couple of things I can think of. Is all my division stuff. And for example, I see the sum is 1112. So the sum of the digits is 12. That means I can actually divide 3 into it. Also, the even and odd positions, I can take 5 plus 1 is 6 and subtract 6. So 11 goes into that too. So maybe let's do 11. So I'm going to do 11 into 561, and this might be not too bad to do mental math wise. There's this nice little sort of like products with 11s in them that you might be able to see. So we've got that. So, but this right away says I've got 11 and 51. All right. And now, even taking this out, that didn't change the 3 in there. And 3, and if you need to do the long division, you can do that. The other piece of that is 17. So we've got that. And the only thing I haven't done is I haven't broken 25 up into 5s. But what this shows me is 14025 is 3 times 5 squared times 11 times 17. So we've got that. Okay. So this is starting to show sort of the power of a lot of the little divisibility tests. Long division is still playing a role because we really want to know what the 2 factors are, which you have to do this. But this shows some examples on that.